Greetings all. Welcome back. Let's do an example of solving a first-order separable differential equation. So here's our example. Find the general solution to the following dy dx equals xy squared. Okay. Strategy for this guy is to note that it is separable. So solve by integration. And again, this idea of writing a simple statement of strategy is going to basically facilitate, one, it organizes your thoughts in order to solve the problem, but it also gives you a chance to reflect later when you're looking at this problem again so that you at least know what it is you were thinking when you actually solved it the first time. So our strategy here is just to, nothing deep, is to realize that we can separate variables here, so let's do it that way. It is a separable differential equation. So our solution will be the following. Here, let's separate the variables. Remember, this is a product of a function of just x, the independent variable, and a function of the dependent variable alone. It's a product of those two. So our h of y in that particular case is y squared, and our g of, well, it's x in this particular example, is just x. So here, let's separate these guys. So this is 1 over y squared dy dx. On the left, we're just dividing out by the y squared, and that guy equals x. Okay? So integrate. We're really integrating with respect to x on both sides. That's actually kind of necessary. So I'll write this over here as one way to think about this, as 1 over y squared dy dx, and that's really with respect to x that we're integrating there. And on this side, it's the antiderivative of x with respect to x. And the reason why we do this is because both of these guys are functions of x. Y is a function of x that we're actually looking for. Its derivative is a function of x. So the entire product is a function of x. And on the right-hand side, obviously, is a function of x. The part that makes this interesting is due to the substitution method, I could rewrite this as nothing more than 1 over y squared dy. Okay, and we'll see for another video a little bit more about why that's true. So really, I can integrate this guy with respect to x, this guy with respect to y. What I'll get is a big expression involving a big equation involving x's and y's, and hopefully we can solve for y in this particular case. Okay, great. So we do the antiderivative here, and we get x squared over 2. There is a constant here. We're going to get a constant for this guy too, and the antiderivative of y to the minus 2 is minus 1 over y. Okay. I could, this might make it a little bit easier since I'm actually going to be solving for y now, and there are many ways to do this algebraically, but I'm just going to write this guy in a slightly different form as x squared plus c over 2. Well, we need to be careful because that's actually a different constant. So I'll make that a different constant as x squared plus k over 2. It doesn't really matter, but until you know what you're doing very confidently or comfortably, it's best to really keep track of all of your constants that are lying around. If I'm going to solve this, I notice that really I can just move this equal sign to the other side. If this equals this, then the reciprocal of this will equal reciprocal of this. And at this point, we can solve for y, and we get y equals minus 2 over x squared plus k, where k is a real constant, and in essence, we've solved our differential equation. Okay. Now, it might be a good idea here to check always a good idea to make sure that you haven't made a mistake along the way. If I were to calculate the derivative of this function that we found, this is minus 2 over an expression involving x. Okay, so the derivative of this particular guy is going to be, we consider this as minus 2 times x squared plus k to the minus 1 power. Right, there'd be a chain rule argument there for taking a derivative. This guy winds up being 2 over, because there's a minus 1 there, x squared plus k squared. Okay, times the derivative of the inside, because remember this is a parentheses x squared plus k to the minus first power. So the chain rule would make us, would be that there's an extra piece to this, which would be another 2x. I can easily write that as, by combining some things, I could write this as x times 2 over x squared plus k, the whole quantity squared. There's a bit of manipulation there with the 4 there and such. And there's one extra x lying around. Of course, that's not going to change if I wrote that as x over minus 2 x squared plus k quantity squared. And that's exactly what our y was. There it is. So this becomes x y squared, and we've solved our differential equation. Okay. The interesting thing here is to keep in mind is this small piece here, where using the substitution method, I can think of this as a function of x, but I can also think of it as, using the substitution method, untangling this so I can integrate with respect to y, but really, we're not really canceling out the dx's here. And keep this in mind, dy dx is not a fraction, so we're not really just basically taking a numerator and a denominator and canceling these guys out. It does work that way in practice, but that's really a factor of the notation involved. That's not really an algebraic thing that's possible to do. Although, in practice, really, once you separate variables, integrating the left-hand side with respect to y, it really is a thing. So there you go. We've solved a differential equation, which was separable first order, through basically just separating the variables and integrating. And that's it for now. Thank you for listening, and we'll speak again very, very soon.